We're going to look at the problem of a block sitting on a frictionless surface, and this block has, say, a hole drilled into it with a spring inside, and we have some kind of projectile, a mass, small mass. So the block's initially at rest, and this mass is initially moving with a velocity directed directly at the spring. So the question is, how far does this spring compress? So spring has a spring constant K, and so what we're looking for is what is the maximum compression of the spring. So as the mass begins, as it comes in and hits the spring and it begins to compress the spring, the large mass will start sliding along this frictionless plane, and eventually, this small mass is going to rebound out or back the other direction, at least relative to the large mass. So the key to this problem is just realizing that at the moment when the spring reaches its maximum compression, the small mass and this large mass, this block, are going to be moving at the same speed. So if you can just picture the moment as this mass moves, if you were to look at motion just relative to the big mass, it's just going to come in, reach the maximum point, and then start moving the other direction. So it'll move. Say if this is the positive direction, it will reach a maximum velocity with respect to its velocity will start out. If this is the positive direction, its velocity will start out larger than this mass, and then it will end by going the other direction, so a negative velocity, so smaller than the velocity of the large mass, which is going to keep moving off to the left. So if it starts with a larger velocity and ends with a smaller velocity, there's a point in there when the velocities are going to be the same, and that's the point that we're interested in. That's the point at which the spring reaches its maximum compression, and so this mass will reach, it'll just be motionless relative to the large mass. Alright, so now that we kind of know what we're looking at, we'll just go the normal route of using conservation of energy and conservation of momentum to get this equation. So if we start with conservation of energy, the initial energy is 1/2, and this is little m, and then we're going to call the initial velocity just v. Alright, and then when they're both going the same velocity, and when the spring is compressed fully, that will have a different velocity, and we can call that we'll just call it v sub e or something like that for equal velocity. Alright, so this is the initial velocity. This will be the only velocity left in the problem. It's the only one given initially, so it'll be the only one left. That's why I'm not going to use a subscript on this. Alright, so this is going to be equal to 1/2 the little mass, and then the e squared, I guess e for equal velocity for both of them. The big M, we will also have that velocity. And then we have to account for the potential energy of the spring. And we'll call X the maximum compression. So say here's the farthest the spring will compress. This distance here is X. Alright, so there's our first equation. And the second one is the conservation of momentum. So we have an mv. Call that the positive direction like we talked about before. Alright, and that's going to be equal to the big M times will be E, V sub E, plus little m. Oops. That's an E. Alright. That's a really messed up. Okay. Alright, so the one way we need to get rid of, we want to solve for X. We're given K and we're given this V. We want to get rid of this V sub E that we introduced into the problem. So go ahead and write this as M plus, so big M plus little m times V sub E. Alright, now if we go back to this energy equation up here, one thing we can do is multiply by 2, obviously, and I'm going to subtract this off on both sides. So okay, so now we just have these two terms left, and I'm going to go ahead and factor out the big M plus little m. Alright, so it's just a bunch of algebra, basically. We pretty much already have the answer. So here, if we, I should have done this in two different colors. Let me switch to two different colors real quick. So I'm going to underline the energy equation in blue, and this is also the energy equation, and the momentum equation I'm going to underline in orange. Alright, I don't know if this is going to help or not, but alright, so now I'm going to work on the momentum equation a little bit. So I'm just going to square it, so m squared v squared equals big M plus little m squared e squared. Alright, so now you can almost just divide these two equations, and voila, the v sub e will go away. So I don't know if this whole color thing helped all that much, because once we combine the two equations, might as well just use black again. But so let me backtrack a little bit with the algebra. Who knows? If we divide this first term, we have a 1 over m minus k x squared over m squared v squared, and then these v sub e's will divide out. 1 over big M plus little m, like that. Alright, yeah, not the best at making the algebra all nice and pretty, but so now we have 1 over little m minus 1 over big M plus little m is equal to this term here, and separate the x squared out. Okay, so we just have to multiply this over, and essentially we're good. So that's on top, we have a k on the bottom, then we have this 1 over little m minus 1 over big M plus little m. Okay, so you can pretty much just take the square root right now. Maybe able to get this into a little bit of a better form with messing with this fraction here. So say we just look at this fraction inside. We have a big M plus little m over little m times big M plus little m minus m over that same thing. Okay, so this part can go away along with this little m right here. Okay, this part is just looking at that part in parentheses. So let's just see if we can simplify this down real quick, get a nice pretty answer. What we have is, alright, and also this downstairs, this little m will cancel with one of those m's up here. So for the part inside the parentheses, we have a big M times the little m that's left over up here times the big M plus the little m. Okay, one of those nice average mass things that turn up a lot. And then downstairs we still have this k, the spring constant, and we're going to take the square root of all of this. We still have this v squared, but that can come outside the square root as just a v. And there we go. So this is, I guess you could say, a prettier form for it. So this is the maximum displacement that the spring will compress as this mass is shot into the hole drilled into this larger mass, all on a frictionless plane. So next time you run across this situation, you'll know just what to do when you're out in the world and you see this thing happen.